mind of God truly be expressed by a single equation? Michio Kaku suggests this divine intellect is but cosmic music resonating through 11-dimensional hyperspace. In this video, we explore why string theory is still fighting to unify the four fundamental forces, transforming our understanding of life into a symphony of vibrating strings. We shall reveal how all biology and chemistry reduce to this one harmonic code, a theory of everything that Einstein himself could not crack. We will show you how this equation holds the secrets to black holes, the evolution of galaxies, and the very origin of existence. Is the universe's final secret destined to be solved by the human mind, or by a quantum machine collaborator? Prepare to journey beyond the limits of conventional physics to the ultimate doorway of reality. Welcome to Quantum Wisdom, Science Beyond Matter. Michio Kaku, theoretical physicist and visionary, has devoted his life to an essential question. Does a single equation exist that can explain everything that exists? This so-called God equation strives to unify the four fundamental forces of the universe: gravity, which holds the cosmos together; electromagnetism, powering our entire technological world; the weak nuclear force, responsible for radioactive decay; the strong nuclear force, holding atomic nuclei intact. All biology reduces to chemistry, chemistry to physics, and physics so far stands on two pillars: general relativity, which describes gravity, and quantum mechanics, governing the other three forces. To merge them is to attain the long-sought theory of everything. This quest is not new. 2,000 years ago, the Greeks pondered the nature of reality. Democritus postulated indivisible atoms, while Pythagoras, observing vibrating strings, glimpsed a mathematical order within music. That ancient vision is reborn today in string theory, where particles are not point-like but tiny vibrating strings. Physics becomes the harmony of these strings, chemistry their melodies, and life itself a DNA quartet. In essence, the universe unfolds as a cosmic symphony, and Einstein's mind of God is nothing more than music resonating through higher dimensions. The magic lies in symmetry. In physics, symmetry means that transformations, such as rotating an object or interchanging particles, leave the equations unchanged. Symmetry reveals beauty, not as ornamentation, but as the universe's essential structure. Every great leap forward in physics has unveiled hidden symmetries, uniting diverse forces under a single law. Einstein once pondered, did God have any choice in creating the universe? For Kaku, the answer is no. Alternate universes in which, for instance, 2 + 2 = 5, are mathematically inconsistent. Our universe, by contrast, is stable, coherent, and unwaveringly precise. It could not have been otherwise. Although we have yet to unveil the final equation, approximate models exist. Kaku proposed a concise version of string theory, known as string field theory. Yet, to complete the picture, we must incorporate membranes, more complex structures whose integration remains one of physics' greatest challenges. Despite these hurdles, physicists believe wholeheartedly that this final equation exists. It will surely be beautiful, elegant, and perhaps no more than a single inch of ink, echoing how E = mc² encapsulates the very secret of stellar energy. Kaku highlights a striking contrast. While literary theory grows ever more complex, physics becomes ever more streamlined. As we peel away layers of cosmic structure, we uncover not chaos, but order, symmetry, harmony, a design so precise it seems inevitable. The universe therefore had no other option. And when we finally uncover this formula, it will stand as the sheet music to the most exquisite symphony ever composed. This potential unifying theory is more than a scientific curiosity. It represents the culmination of centuries of human thought, a thread that links ancient philosophers to modern physicists. Kaku reminds us that the laws of nature are not man-made inventions. They are discoveries waiting in the fabric of reality. Just as Newton did not invent gravity but revealed its law, so too might this final equation be unveiled, not written by us, but written into the universe itself. The pursuit is not simply intellectual, it is existential. In searching for this equation, we are in fact searching for ourselves, for our place in the grand design. But this is more than science. It is also a deeply philosophical and spiritual vision. Kaku revisits the question that so consumed Einstein. Can the mind of God truly be expressed by an equation? For Kaku, that mind is not mystical. It is the universe's own mathematical expression, laws so universal that any advanced civilization, even in another galaxy, could discover them. Words in a different language perhaps, but the same truth. Just as E equals mc squared revolutionized our understanding of energy, so the final equation will be equally brief, yet contain the entire structure of the cosmos, from atoms to galaxies, from the Big Bang to consciousness. Kaku believes that we are tantalizingly close to achieving it. But remember, this triumph is about more than solving an equation. It is the human attempt to comprehend our existence within a mathematical architecture. Rather than diminish wonder, modern physics elevates it to a sublime form of understanding. Michio Kaku invites us to ask one of the most provocative questions in modern physics. What preceded the Big Bang? Is time travel possible, or could we traverse wormholes into other universes? While these ideas read like science fiction, Einstein's equations do not forbid them. General Relativity, in its full mathematical richness, provides solutions that allow for wormholes and even time machines. But the key question is not whether they are theoretically possible, but whether they are physically realistic. To construct a stable wormhole or time machine would require energy on the scale of a black hole, an astronomical amount, and even then, there is no guarantee such a structure wouldn't collapse or self-destruct the moment it is entered. Stephen Hawking, for instance, believed that any attempt to use a time machine would destabilize it instantly. Since these ideas derive solely from Einstein's theory, we need to go further. Enter string theory. Our best candidate to reconcile all four fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. String theory introduces the necessary quantum corrections to explore these extreme phenomena. Can a wormhole remain open? Will quantum effects cause it to collapse? Quantum mechanics brings a new twist, the principle of superposition. If you travel into the past and alter an event, you do not overwrite your original timeline. Instead, the universe branches like a river dividing into two. You may have saved Abraham Lincoln, but only in an alternate universe. This is the core of the many worlds theory. We occupy one bubble in a vast ocean of universes. This metaphor aligns with the Big Bang. Our universe expands like the surface of a bubble. But this analogy becomes even more profound when we consider what lies beyond that bubble. String theory suggests the presence of additional spatial dimensions beyond the familiar three of length, width, and height. These extra dimensions may be tightly curled up, invisible to us, yet crucial in explaining the fundamental behavior of particles and forces. In some versions of the theory, entire universes might be stacked like pages in a book, separated only by fractions of a millimeter, unreachable by current technology, yet mathematically consistent. If true, this would not only confirm the multiverse, but also open the door to radical ideas, parallel histories, mirror realities, and even versions of ourselves that made different choices. The cosmos, it seems, is not a singular narrative, but a library of infinite possibilities. Inflation theory deepens the picture. It suggests that, in its infancy, the universe experienced a rapid burst of expansion, an inflationary moment. Once quantum mechanics is applied to inflation, the process becomes eternal. Expansion never stops. Bubbles of space, new universes, sprout indefinitely. While you listen to these words, other universes may be emerging, hidden in dimensions beyond our own. Naturally, this invites questions that feel curious, but are scientifically valid. Is Elvis Presley alive in another universe? According to many worlds, yes, because if something can happen, it happens somewhere. But is this science or philosophy? Kaku reminds us that science demands explainability, reproducibility, and falsifiability. Inflation theory, though still incomplete, has robust experimental support and is part of the standard cosmological model. By contrast, the many worlds interpretation lacks direct empirical proof. Another perspective comes from physicist Eugene Wigner. Every experiment requires an observer. This prompts the question, who observes the observer? Wigner suggested an infinite chain of observers, which could only terminate if a supreme consciousness, some call it God, exists. Wigner later embraced Hindu mysticism to explain this. Kaku, however, finds the many worlds interpretation more satisfying than that mystical option. Yet, the most powerful critique of string theory is the landscape problem. It predicts vast numbers of possible universes, some stable, many chaotic, and countless empty. It fails to explain why we happen to live in a life-permitting universe, rather than one of the unstable ones. Kaku draws an analogy with Maxwell's equations. These allow for infinite possible solutions, countless light bulbs, lasers, and electrical systems. Nobody complains about them. So why worry if string theory predicts infinite universes? The only difference lies in scale. Instead of billions of light bulbs, we're talking about billions of universes, but the principle remains the same. If we knew the initial conditions of our Big Bang, we could use string theory to identify the precise solution that corresponds to our universe. Towards the end, Kaku reflects on the universe's stability. Newtonian physics, the physics of everyday intuition, produces unstable orbits. Planets and comets eventually collide or fall into stars. Without quantum mechanics, atoms themselves would collapse. How does quantum stabilization occur? By allowing electrons to exist in multiple locations simultaneously. What we learn as orbitals in school chemistry is a direct manifestation of this quantum strangeness. Matter remains stable precisely because, in a sense, we are coexisting with parallel universes. If this strikes you as odd, get used to it. As Michio Kaku reminds us, this is how the universe truly works. Michio Kaku takes us on a captivating journey through the history of science, from the ancient Greeks to string theory, with one unified aim: to find a single equation capable of describing the entire universe. The voyage begins in the 17th century, with Isaac Newton and his groundbreaking theory of gravity. Moving into the early 19th century, Michael Faraday discovered that changing magnetic fields generate electricity, and vice versa. Soon after, James Clerk Maxwell tied these insights together in his celebrated electromagnetic equations, demonstrating that light itself is an oscillation within the electromagnetic field. Following the advent of the atomic bomb, physicists turned their attention to nuclear forces. This led to the discovery of quarks, gluons, quantum electrodynamics, and quantum chromodynamics, culminating in what we now call the Standard Model. Although extraordinarily precise, the Standard Model is conceptually awkward. It includes 36 quarks and antiquarks, 21 adjustable parameters, and 3 nearly identical generations of particles. Kaku likens it to a platypus, an anthieta, and a giraffe stuck together with tape. It works, but it's clearly not the final theory. This is where string theory enters the picture. Unlike the Standard Model, which omits gravity, string theory not only includes it, but requires it. Kaku explains that even if Einstein and relativity had never existed, string theory would still have produced gravity as the lowest vibration, the fundamental note of a string. That vibration encodes the mathematical score behind curved space-time. A crucial question then arises. What experimental evidence supports something this ambitious if we cannot directly access Planck scale energy? Kaku offers a classic reply. Much of physics relies on indirect verification. We don't need to enter the sun to understand its composition. We deduce it by analyzing the light it emits. Similarly, we don't require a galaxy-sized collider. It would suffice if string theory could derive the mass of the proton, the electron, or any known particle from first principles. If it did, the argument would be concluded. We would have arrived at the theory of everything. In fact, some researchers argue that string theory could do more than just unify forces. It might predict entirely new forms of matter or reveal dimensions of space hidden from our current perception. These extra dimensions, though curled up tightly beyond detection, could influence the fabric of reality in subtle yet measurable ways. If verified, such predictions would elevate string theory from an elegant framework to the definitive map of the cosmos. Moreover, string theory provides explanations for deeply mysterious phenomena such as dark matter. The higher vibrations of strings could harbor the invisible particles that make up 95% of the universe. From this vantage, visible matter, like us, is the exception. Dark matter is the rule. Kaku reminds us that most of physics is founded on indirect evidence. We observe star spectra or molecular energy levels in DNA without ever touching them. In the same manner, we could validate string theory by detecting predicted effects, new particles, subtle alterations in space-time structure, or signals in dark matter detectors. Ultimately, if string theory could derive from a minimal set of equations, the fundamental properties we observe, mass, charge, interactions, it would transform itself into the theory of everything. No further experiments would be needed. It would be akin to discovering the source code of the universe. Thus, Michio Kaku invites us to dream of that final formula, the fabled God equation, a single, elegant equation that would enable humanity to read the mind of God, echoing the vision of Albert Einstein himself. Michio Kaku invites us to envision reality as a vast cosmic chess game. Physicists may not yet be grandmasters, but they are diligently learning the rules of the game: gravity, electromagnetism, and the nuclear forces. Each piece on this cosmic board follows precise moves, patterns we have been striving to decode for centuries. Yet knowing the rules does not mean we understand the strategy. Here emerges a striking idea. Consciousness, love, even the soul might be emergent properties, impossible to deduce directly from the underlying physical laws. This challenges reductionism and suggests that even if we achieve the equation of God, a formula that encapsulates all physical laws, there would still remain realms of existence to explore at higher levels of being. Kaku is unambiguous. Even with this ultimate equation in hand, physicists will not be out of work. Their real task will be to decipher how that elegant formula gives rise to phenomena as profound as human awareness. He also addresses one of humanity's most profound existential questions. Does the universe have meaning? When confronted with dark cosmic destinies, such as the Big Freeze or the Big Crunch, certain scientists fall into nihilism. Steven Weinberg, for instance, declared, "The more we understand the universe, the more we see how meaningless it appears." But Kaku offers a hopeful synthesis of science and spirituality. He draws upon two contrasting worldviews from his youth: Buddhism, which recognizes no beginning or end, and Christianity, rooted in Genesis. He finds symbolic reconciliation in the Big Bang model. The universe began like an expanding bubble within an atemporal hyperspace. In this vision, our universe has a beginning, but that origin lies within something far greater, what he calls a physical nirvana. Within this framework, meaning is not something we are given. It is something we build. The very pursuit of understanding our place in the cosmos becomes a source of purpose and wonder. Discovering the final equation would not mark the end of our quest, but rather the start of an even deeper exploration. That equation would be the grammar of the universe, but we humankind must write its poetry. Even the phrase equation of God, intentionally provocative, serves to bring science closer to the public. Kaku recalls the moment when the superconducting super collider was proposed in Texas. A congressman asked whether it would find God, and the physicist answered coldly, "Higgs boson." The project was then cancelled. Kaku reflects, had they described it as a Genesis machine, capable of recreating the birth of the universe instead of merely seeking a particle, the narrative might have been heard with awe, not dismissed as yet another technical endeavor. In Kaku's eyes, scientists must learn to speak in human terms. Data alone will not suffice. People need context that tells them, yes, there is a place for you in this vast cosmos. Michio Kaku offers a profoundly inspiring and provocative vision. A theory of everything might not only explain the universe, but also offer salvation from its inevitable demise. Imagine this God equation as a lifeline against cosmic extinction. For decades, physics has warned of two extreme fates: the Big Freeze, where the cosmos expands indefinitely, stars die out, black holes evaporate, and utter darkness prevails. The Big Crunch, where everything collapses back into a singular point. Both scenarios seem inevitable under the second law of thermodynamics. All systems tend toward decay, dispersion, and entropy. The universe appears doomed to oblivion. But what if there's an out? That law applies only to closed systems. Suppose our universe is enclosed, and there exists a hyperspace shortcut to another cosmos. Kaku envisions a distant future where mastering Planck energy, the energy scale of the Big Bang, enables humanity to produce space bubbles, portals opening into new universes. Not water bubbles, but bubbles in space-time that could launch a fresh genesis when ours grows old, cold, and silent. Where does this power originate? From first principles, the total angular momentum of the universe is zero. Total electric charge, positive and negative, is zero. The positive energy of matter and the negative energy of gravity cancel each other. Our universe has zero net energy. It might truly have emerged from nothing. Stephen Hawking termed this quantum foam of space-time, a microscopic, perpetual bubbling where minuscule universes flicker in and out of existence. The multiverse isn't just out there. It's within every atom of us, an infinite tapestry of possibilities woven into the fabric of reality. So how might we access these hidden dimensions? Through the bold, new frontier of quantum computing. Kaku traces its evolution. Analog computers, like Babbage's mechanical gears. Digital computers, inspired by Alan Turing's transistor-based binary logic. Now, quantum computers, leveraging the non-binary nature of reality, waves, probabilities, and superposed particles. Richard Feynman, pioneer of quantum electrodynamics, dared to ask, how small can a transistor be? The answer? One atom. Quantum computers operate across many parallel universes simultaneously because electrons can occupy multiple states at once. This gives qubits an exponentially higher computational capacity than classical bits. This is no distant dream. Governments and major corporations are racing to build these machines, for good reason. They can break nearly any code, solve today's impossible problems, and revolutionize medicine, energy, and agriculture. Precisely simulate molecules behind Alzheimer's and cancer. Harvest nitrogen from air for sustainable fertilizers. Control nuclear fusion for clean energy. All thanks to quantum coherence, a capability nature already uses. Plants use it to perform photosynthesis at room temperature. If nature can master coherence, so might we. Of course, challenges remain. Decoherence, the loss of electron synchrony, threatens computation. That's why these systems operate near absolute zero. Yet the potential is vast. Kaku emphasizes that mastering quantum physics will reshape not only our knowledge, but our relationship with the universe. Just as the microscope unveiled hidden worlds, quantum computing may uncover the code of existence. Within that code, we may unearth the story of our future. Kaku concludes with a personal hope that these technologies will help us unlock the unified theory of the universe, that calculations so complex Einstein never solved may one day be executed not by human intellect but by a quantum machine's memory. However, Kaku emphasizes that this is not mere speculation. It is already gaining tangible traction. National governments and major corporations are actively investing, pushing the frontiers of research and development. Their motivation is clear. Quantum machines can fundamentally break existing cryptographic schemes, redesign pharmaceuticals through molecular-level simulation, and revolutionize industrial processes such as nitrogen fixation and fusion control. He cites the phenomenon of quantum coherence, a property that, astonishingly, occurs naturally in photosynthesis at room temperature. If nature can sustain coherence in warm, wet environments, human ingenuity might learn to replicate it in engineered systems, thus overcoming the chilling challenge posed by decoherence. Kaku further notes that as qubit counts grow, reaching into the thousands and eventually aiming for 1 million, quantum computers become capable of tackling problems that are hopeless for classical machines. These include optimizing complex logistics, cracking the secrets of dark matter, and even exploring the quantum nature of space-time itself. In this light, the quest for the God equation becomes intertwined with quantum computation. Not only might we solve that ultimate unified theory, but we may do so using the very machines that harness the subtle, parallel unfolding of reality, a poetic convergence of theory and technology. And perhaps, when the universe nears its end, we will already be building a new beginning. Michio Kaku presents a powerful idea. The God equation is not merely a scientific formula. It might be the strongest argument for the existence of God, understood not as a religious figure, but as the embodiment of mathematical harmony within the universe. Although Kaku identifies as agnostic, he does not shy away from the spiritual dimensions of this quest. He believes that a 1-inch long equation capable of describing all physical laws would be the ultimate proof that the universe is governed by a hidden order, elegant, beautiful, and intelligible. This is not a personal or pantheistic deity, but rather a rational ideal, a cosmic pattern of symmetry and coherence. Kaku refers to it as an expression of a fundamental integrated beauty, transcending traditional religious boundaries. To illustrate this, he recalls a defining episode, the superconducting Super Collider project, planned for Texas in the 1990s. During a congressional hearing, a senator asked whether the collider would find God. The physicist in charge answered, "No, but we'll find the Higgs boson." A technically accurate, yet emotionally sterile response. The project was cancelled. $2 billion went into digging a hole, only to later fill it in. American physics lost a generation of progress. Kaku reflects, what if the answer had been different? What if we had said that this machine could recreate the moment of Genesis, that it could glimpse the birth of the universe? Perhaps then, that hole would have symbolized not just lost funding, but humanity's shared longing to understand its origins. For Kaku, the lesson is clear. Science must relearn the language of symbolism and wonder. It must engage with the timeless questions. Where do we come from? What are we? Where are we going? This isn't a call for superstition. It's a call for a new kind of scientific storytelling, one that unites precision with purpose, data with meaning. In Kaku's view, the most transformative scientific ideas are those that also resonate on a human level. Equations are important, but without a story to tell, they risk becoming sterile. The God equation, he believes, must inspire awe as well as calculation. Kaku doesn't claim the God equation will give us personal answers or eternal happiness. But he does offer a new narrative, a science that inspires, connects, and enlightens. Because in the end, as Kaku insists, even if physics understands more than ever before, it must never lose its connection to mystery if it wishes to remain meaningful to the human soul. For Michio Kaku, digital computers change the world, but quantum computers promise an even deeper transformation. We now stand at the threshold of a new era, the age of the ultimate machine, not one powered by transistors, but by atoms, the fundamental building blocks of reality itself. This global race involves every major player, tech giants, world governments, including the FBI, CIA, and national security agencies, and top cybersecurity firms. Missing this wave means risking obsolescence. Even Silicon Valley, once untouchable, could become the next Rust Belt. Why such urgency? Because quantum computers won't merely enhance science or the economy. They could crack virtually any digital code and redefine how we approach problems across every industry. Kaku breaks it down like this. We began with analog machines, like the mysterious mechanism discovered on a shipwreck dating back 2,000 years, designed to model the moon and planets. Later came the mechanical inventions of Charles Babbage, complete with gears and cranks, used to calculate latitudes and interest rates. Then came World War II, ushering in the digital age through Alan Turing's binary-based transistor computers. Each step was revolutionary. But now, a new revolution has arrived, the quantum age. Unlike a digital bit, which can only be 0 or 1, a quantum bit, a qubit, can exist in a superposition of all possible states. Think of Schrödinger's cat, alive and dead at once, until observed. Qubits, much like that thought experiment, operate across multiple realities simultaneously. This ability allows quantum computers to compute in countless parallel universes at once, offering power that grows exponentially. We've already achieved quantum supremacy for specific tasks. The new challenge is building machines that outperform any digital computer across the board, and we're closer than ever. The main hurdle: decoherence. Qubits can lose synchronization and collapse into noise. To avoid this, quantum machines operate near absolute zero, but nature already achieves coherence flawlessly. Photosynthesis in plants, for example, is a quantum process that works at room temperature. If nature can do it, surely engineers can learn from it. The potential is staggering. In agriculture, quantum models could extract nitrogen from air to produce eco-friendly fertilizers. In energy, they may stabilize nuclear fusion. In healthcare, they might simulate molecules linked to Alzheimer's, Parkinson's, or cancer, offering a path to treatments once thought impossible. But beyond the lab and server racks, quantum computing also raises fundamental questions about intelligence itself. Could a quantum machine ever become self-aware? Might it understand the problems it solves, or even participate in formulating questions we've never thought to ask? These aren't idle speculations. Some physicists suggest that consciousness could be a quantum phenomenon, one that current AI cannot replicate. If so, then quantum computing isn't just the next step in technology. It's a doorway into a deeper comprehension of mind, thought, and perhaps reality itself. In this vision, quantum computers aren't mere tools. They could become collaborators, co-discoverers of the universe's most intimate secrets. With them, humanity may not just solve equations, but uncover new realms of meaning, bridging science and philosophy in ways never imagined. Kaku envisions a day when quantum computers solve equations Einstein himself couldn't crack, a unified theory explaining black holes, supernovas, even the evolution of galaxies. And perhaps that final theory won't be born from the human mind, but from the memory of a quantum machine. And that concludes our video. If you enjoyed the content as much as we did, don't forget to subscribe so you don't miss a single episode. Leave a comment below. We'd love to hear your feedback and suggestions for future videos. And don't forget to turn on notifications to stay up to date with all our updates. Thanks for being part of our community. See you in the next video.